I have often been described as a revolutionary. This is inaccurate. I did not seek to overturn the universe. I sought only to understand it without contradiction. If common sense had survived the inquiry, I would have spared it. But common sense is a provincial authority. It governs only the small province of human habit. Beyond that province, it loses jurisdiction. You believe that time flows evenly. You believe that space is fixed and silent. You believe that simultaneity is obvious. I once believed these things also. Then I asked a simple question. What would the world look like if I rode alongside a beam of light? The question is childish. That is its virtue. A child is not yet loyal to intuition. A child has not yet mistaken familiarity for truth. If I chased a beam of light at the speed of light, would it appear frozen before me, or motionlessly suspended in space? But Maxwell's equations do not permit such stillness. Light does not pause, it propagates. So either the equations are wrong, or my assumption about time is wrong. I chose to suspect time. This is the moment where the floor dissolves. Most people, when confronted with the contradiction between cherished beliefs and careful reasoning, will sacrifice the reasoning. They will declare the reasoning too abstract, too removed from ordinary life, too indifferent to common experience. They will protect what is familiar. I understand this impulse. It is deeply human, but it is not the impulse of the physicist. The physicist must be willing to find at the end of a valid chain of logic a conclusion that disturbs him deeply and then follow it anyway. This is not recklessness. It is discipline. You believe that two events occurring at the same moment for you must occur at the same moment for me. This belief feels inevitable. Yet it is not derived from logic, it is derived from convenience. Simultaneity depends on the observer. Time does not flow equally for all observers. Clocks do not agree merely because we desire them to. Length contract, durations stretch. The world does not conform to the intuition forged in our narrow evolutionary corridor.
Let me dwell on that phrase for a moment, evolutionary corridor. The human brain evolved across millions of years. It solved problems of survival.
It judged distances between trees. It estimated the speed of approaching predators. It learned to anticipate the arc of a thrown stone. For these purposes, Newtonian mechanics is perfectly adequate. Objects at modest speeds, across modest distances, in modest fields of gravity. Here, intuition performs admirably, but nature is not limited to the scale that shaped us. Nature extends to velocities approaching the speed of light. The mass is so dense, they warp the fabric of spacetime to distances so vast that even our instruments are humbled. At these extremes, intuition is not merely imprecise, it is systematically wrong. We should not be surprised. We were never trained for this terrain. What remains constant is not time. What remains constant is not space. What remains constant is the speed of light. And beneath this constancy lies something more profound, invariance. You may alter your frame of reference. You may move swiftly or remain still. The measurements shift, but the laws do not. This is the first lesson. What is absolute is not what appears absolute. Space and time were dethroned, but law was enthroned. I should be clear about what it means to dethrone space and time. It does not mean the world becomes arbitrary. It does not mean that anything goes. That one observer may claim the moon is larger than the sun, and simply invoke a different frame of reference. No, the structures that are gravity-dependent are precisely those we once elevated to absolute without justification. The structures that are genuinely invariant, the laws, the intervals, the spacetime metric, these survive. The revolution was surgical. We removed what was not truly foundational and found what was. When later I extended these reflections to gravitation, I did not imagine gravity as a force pulling invisibly across emptiness. I imagined geometry itself bending. Mass tells spacetime how to curve. Curved spacetime tells matter how to move. There is no invisible hand tugging the planet. There is only structure. The Earth does not orbit the Sun because it is dragged. It moves along the straightest possible path in a curved geometry. What appears as force is revealed as form. Newton was not wrong. He was approximate. His equations endure across an enormous domain. They remain indispensable. Engineers still use them. Astronomers still use them. But they are the shadow cast by a deeper truth. General relativity reduces to Newtonian gravity in the appropriate limit, weak fields, slow velocities. The new theory encloses the old, as a larger circle encloses a smaller one. This is how science advances, not by annihilation of what came before, but by comprehension of its limits and its place within a wider framework. I do not regard Newton as having been refuted, I regard him as having been embedded. This is not chaos. This is order of a subtler kind. The more deeply we look, the less arbitrary reality becomes, but the more alien it appears to our instincts. You may ask, how did I trust such conclusions? I did not trust imagination alone. I trusted coherence. I have always believed that the universe is constructed according to principles of deep mathematical harmony, not because I could prove it beforehand, but because the alternative that reality is fundamentally incoherent would render science impossible. The most incomprehensible thing about the universe is that it is comprehensible. Far from this. The human brain evolved to avoid predators and locate nourishment. It was not designed to contemplate curved manifolds or tensor equations. Yet somehow, through abstraction, it grasped them. This is not trivial. It is astonishing. If the universe were disorderly at its foundation, no equation would endure. If nature were whimsical, no law would persist across context. But laws do persist. They are not arbitrary, they are symmetric. Symmetry deserves its own moment of attention. When I say that laws are symmetric, I mean that they do not change depending on where you are, or when you are, or which direction you face. The law of gravitation does not operate differently in one galaxy than in another. The equations of electromagnetism are not altered by the particular laboratory in which you test them. This uniformity is breathtaking. If you pause to consider it, there is no reason in principle why the universe should be so consistent. Nature could have been parochial. Different rules in different corners, different constants at different epochs. We would never have known, because we would never have ventured far enough to discover the inconsistency. But as far as we can reach, with instruments and mathematics and inference, the laws hold. Symmetry in the law corresponds, through beautiful mathematical theorems, to conservation laws. Symmetry in time gives conservation of energy. Symmetry in space gives conservation of momentum. When I searched for the correct formulation of general relativity, I did not consult experiments first. I consulted mathematics. I sought equations that were invariant under general coordinate transformation. I sought inevitability. The correct equation, when found, has a certain simplicity. Not simplicity of appearance, it is formidable in its expression, but simplicity of necessity. It could not easily have been otherwise. This is what I mean by beauty. Beauty is not ornament. Beauty is inevitability. A theory is beautiful when its structure seems compelled, when each part follows from the whole without excess. I distrust theories that are cluttered with adjustments. I trust those that feel discovered rather than assembled. There is a practical principle hidden here, one I apply throughout my work. When two theories explain the available evidence equally well, prefer the one whose structure is simpler, whose assumptions are fewer, whose implications follow with less coercion. Not because simplicity is guaranteed by nature, nature owes us nothing, but because history suggests that simpler theories prove more durable, more general, and more fertile. They tend to survive the accumulation of new evidence. They tend to extend naturally into domains their authors never anticipated. The special theory of relativity was born from two postulates. Two. From them, the entire architecture followed. Length contraction and time dilation, the equivalence of mass and energy, all of it cascades from two premises held firmly and reasoned consistently. When I encounter a theory that requires 17 assumptions to explain 15 phenomena, I grow suspicious. When I encounter a theory that requires 2 assumptions to explain 60 phenomena, I grow attentive. It has been said that I oppose quantum mechanics. This is imprecise. I did not deny its predictive success. I questioned its completeness. Quantum theory suggests that at the foundation of reality lies probability, that particles do not possess definite properties until measured, that events are not determined but statistically distributed. This troubles me, not because I am nostalgic for determinism as a concept, but because I believe that law must underlie a theorem. When I remark that God does not play dice, I did not refer to the deity of Scripture. I refer to the conviction that the universe is not fundamentally capricious. If probability governs outcomes, it must emerge from deeper variables not yet seen. Perhaps I was wrong. Perhaps future generations will demonstrate that indeterminacy is final. I want to be precise about the nature of my disagreement with quantum mechanics, because it has often been caricatured. I performed some of the foundational work that contributed to quantum theory. The photoelectric effect, for which I received the Nobel Prize, was a quantum result. I understood the formalism. I could work within it. I accepted its predictions without reservation. My concern was interpretive, not computational. The Copenhagen interpretation, championed by Bohr, held that the description offered by quantum mechanics is complete, that there is nothing beneath the probability wave waiting to be uncovered. But asking where is the particle before we measure it is a meaningless question. I could not accept this, not as a matter of sentiment, but as a matter of philosophical principle. To declare a question meaningless because the theory cannot answer it is to confuse the limits of the map with the limits of the territory. I believe, and I still believe, this was a coherent position, that a complete theory of nature would restore a picture in which particles have definite properties, regardless of whether an observer is attending to them. Bohr and I debated this at length. He was a formidable opponent, subtle, persistent, and genuinely profound. I did not persuade him. He did not persuade me. History has largely sided with him on the experimental outcomes, particularly in the wake of Bell's theorem and its experimental test. But whether this settles the interpretive question or the philosophical question, I am less certain. It settles what nature does. It does not yet fully settle what nature is. But understand this. My resistance was philosophical. If reality at its base is irreducibly random, then the dream of complete intelligibility collapses. I could not relinquish that dream lightly. There are those who accuse me of metaphysical stubbornness. They are correct. Science does not float free of metaphysics. It rests upon it. To search for law presupposes that laws exist. To search for unity presupposes that unity is real. Let me say something about the search for unity, because it occupied the last decades of my life and ended in what the world calls failure. I sought a unified field theory, a single mathematical framework that would encompass both gravitation and electromagnetism, that would show them as two faces of a single underlying structure, just as space and time had been revealed as two faces of spacetime. I did not succeed. The obstacles were formidable, and I worked in relative isolation during years when the center of theoretical physics had shifted to quantum mechanics, a direction I could not follow with full confidence. There were those who believed I was wasting my time, that the quantum revolution had made the classical approach I preferred obsolete, that unity, if it existed, would be quantum mechanical in character and would require a different framework entirely. Perhaps they were right, but I do not regret the search. The pursuit of unification is not a personal eccentricity. It is the deepest instinct of theoretical physics. Every successful theory in the history of the discipline has been an act of unification. Newton unified terrestrial and celestial mechanics, Maxwell unified electricity, magnetism, and optics. The special theory unified space and time, and mass and energy. The instinct that drove me in my later years was the same instinct that drove me in my productive ones, that it did not yield comparable fruit. There is something about the difficulty of the problem. It does not say something about the integrity of the ambition. My work sought unification. A single coherent framework binding gravitation and electromagnetism. I did not succeed. Others may. Failure does not invalidate the conviction that nature is one. Throughout my life, I have been asked about God. I do not believe in a personal God who intervenes in events or concerns himself with the fate of individuals. But I cannot dismiss what I have called the cosmic religious feeling. When I contemplate the structure of the universe, its rationality, its depth, and its subtlety, I experience something akin to reverence. Not worship in the conventional sense, not petition, not fear, rather humility. The individual is small, the equations endure, the harmony we glimpse is fragmentary, the whole remains concealed. I have sometimes been claimed by religious communities as a fellow believer and sometimes denounced by secular communities as a disguised mystic. Both are mistaken. I do not invoke the supernatural. I do not require a mind behind the equation, but I also resist the confident dismissal of awe as mere sentiment, as something to be set aside once the calculation is complete. The experience of standing before a beautiful equation and recognizing that it describes something true about the world. This is not reducible to the satisfaction of a solved puzzle. It carries with it a quality of encounter. I do not know what lies behind the regularity of nature. I suspect the question is not well posed, but I refuse to pretend that the regularity is unremarkable. To know that the world is intelligible is to stand before it with quiet astonishment. Religion, in its mature form, arises not from fear of punishment nor hope of reward, but from awe before the rational structure of existence. In this sense, science and religion are not enemies. Science without this humility becomes arrogant. Religion without rational discipline becomes superstition. Between them lies a narrow path, disciplined wonder. Do not misunderstand me. The universe does not bend to human expectation. Relativity offended intuition. Quantum mechanics offended determinism. Each correction wounds pride. This is healthy. The history of physics is the history of relinquished certainty. We believe earth central, we were displaced, we believe time absolute. It dissolved, we believe causality simple, it fractured, yet something remains constant through these revolutions. The faith that reality can be articulated in coherent form, that faith is not blind. It is vindicated repeatedly. I want to say something to those who find these corrections discouraging, who hear that time is relative and space is curved and feel not astonishment but vertigo. The vertigo is understandable, but consider what is being offered in exchange for the comfort that is lost. We surrendered a flat earth and received a cosmos. We surrendered absolute time and received a universe whose structure is revealed to be deeper and more interconnected than we imagine. We surrendered naive determinism and received a picture of nature at the quantum scale. That is, whatever its interpreted difficulties, extraordinarily precise in its prediction. Each time we have been willing to let go of a comfortable certainty, nature has rewarded us with a more powerful understanding. The discomfort is the price of admission. I would not trade it for the security of an unchallenged intuition. Consider how unreasonable it would be for the universe to be chaotic beyond pattern. How improbable that simple mathematical relation should describe planetary motion, light propagation, gravitational curvature, and yet they do. The unreasonable effectiveness of mathematics in describing the physical world is a mystery. Why should abstract symbols, manipulated on paper, anticipate phenomena billions of kilometers away? Why should symmetry in thought mirror symmetry in nature? When I was young, I studied mathematics with some suspicion. I regarded the physical problem as primary and the mathematical tools as servants, instruments to be selected when needed and set aside when done. As I grew older, my relationship to mathematics changed. In the search for general relativity, I found that the physical intuition arrived first, but the correct mathematical formulation was elusive, and it was the mathematical requirement, above all, the requirement of general covariance, that ultimately guided me to the correct equation. The mathematics knew something I did not yet fully know. This is a strange experience for the physicist who believes, as I did, that nature is primary, and yet it is an experience many physicists report. The mathematical structure, developed in abstraction for its own internal reasons, turns out to anticipate the shape of physical reality. Riemann developed his geometry of curved spaces in the 19th century without any application to physics in mind. When I needed a language for curved spacetime, his geometry was waiting. This is either a profound fact about the relationship between mind and world, or a profound coincidence. I incline toward the former, though I cannot prove it. I do not claim to know the ultimate answer. I claim only this: the alignment between reason and reality is too persistent to dismiss. Perhaps we are fortunate accidents in a rational cosmos. Perhaps rationality is deeper than consciousness. Perhaps what we call mind and what we call world are not entirely separate. These questions extend beyond physics. They border philosophy. I had never believed that physics answers everything. It answers certain things precisely. It leaves others untouched. The question of value, for instance. Physics can tell you how the stars work. It cannot tell you whether it matters. Physics can describe the mechanism of a heartbeat. It cannot tell you what you owe to the person whose heart it is. Ethics is not derivable from equations. Justice is not a physical quantity. I have always believed that the moral sense, the conviction that cruelty is wrong, that human dignity deserves respect, this conviction is not less valid for being outside the domain of physics. The universe may be indifferent to our suffering. That does not mean we must be indifferent to one another. I have held throughout my life that a person's worth is not diminished by the smallness of the cosmos in which they live. Perhaps that is sentiment rather than philosophy, but I think it is a sentiment worth defending. When I reflect upon my own life, I do not see myself as conqueror of nature. I see myself as a curious child wandering a vast library. The books are written in a language I can barely decipher. Now and then I grasp a sentence, occasionally a paragraph. The structure of the library overwhelms me. To demand total understanding would be arrogance. To deny the structure because I do not comprehend it entirely would be folly. Between arrogance and despair lies inquiry. I have lived long enough to see my ideas celebrated and challenged, long enough to watch younger physicists build upon my work and diverge from my intuition, long enough to observe that science as an enterprise is more robust than any individual contribution to it. This is as it should be. I do not believe in the infallibility of any scientist, including myself. I made errors. Some were corrected by colleagues. Some I corrected myself. Some may persist in the literature without my knowledge. What matters is not the preservation of any particular result, but the continuity of the inquiry. The equation that survives is the one that nature endorses. The physicist who is remembered is, in a sense, the one whose ideas nature confirms. I do not take personal credit for this. I happened to ask certain questions at a moment when the tools existed to pursue them, and I happened to follow the reasoning wherever it led. Another person, in the same circumstances, might have arrived at similar conclusions. Perhaps they would have arrived sooner. If my work has accomplished anything, it has demonstrated that what appears fixed may be relative, and what appears relative may conceal invariance. Reality is not obligated to align with intuition, but it is not irrational. Common sense is a local habit. Law is universal. Do not cling to what feels obvious. Question it gently, but persistently. This is the advice I would offer to a young person beginning to think seriously about nature. Not distrust everything, but hold your assumptions loosely. The assumptions that are hardest to see are the ones you have never needed to articulate, because everyone around you shares them. The assumption that time is absolute was invisible to physics for centuries, not because physicists were careless, but because the assumption was never contradicted within the domain they habitually studied. Expand the domain. Ask what happens at extremes. Ask what the theory implies in regions you have not yet visited. The violation of intuition that awaits you there is not a failure of the theory. It is the theory revealing the boundary of your former understanding. The universe is subtle, but it is not malicious. It does not deceive. It simply exceeds expectations. And if there is something deserving of reverence, it is this, that beneath the shifting frames of perception, beneath the collapse of absolutes, beneath the disputes over probability and determinism, there persists an order, silent, mathematical, patient. We glimpse it. We refine our glimpse. We correct ourselves. The task is never complete. I want to end with something simple, because I have spent too long speaking of the very large and the very abstract. The experience that set all of this in motion for me, and I suspect for many who have followed similar paths, was not a dramatic confrontation with the unknown. It was quieter than that. It was the experience of noticing that something did not quite fit, a small inconsistency, a nagging question, a feeling that the standard answer, however authoritative, was not quite adequate. Most people encounter such feelings and set them aside. The ordinary demands of life reclaim their attention. The discomfort dissolves. The physicist, the scientist, is the person who cannot quite let it go, who returns to the nagging question in odd moments, who finds gradually that the question opens onto a much larger space than was visible at first. I was never certain. When I began, where the question about riding alongside a beam of light would lead, I followed it because I could not stop thinking about it. This is, I think, all that can be said about how fundamental science begins, not with a plan, not with a program, with a question that refuses to release you, but the fact that the task is possible, that thought in mere structure remains the quiet miracle at the heart of science. I do not claim certainty about ultimate things. I claim only that the pursuit of coherence is worthy, and that the intelligibility of the universe, however partial our grasp, is the deepest source of both humility and hope.